In the almost empty darkness, a vast cloud of gas does not fall straight, but begins to swirl. Seen from far enough away, the universe looks like a room where almost everything is rotating. Planets spin on their axes, moons orbit planets, and young stars often form with rotating disks of matter. Around black holes, matter also does not fall straight into darkness, but swirls into a blazing hot disk. On a larger scale, entire galaxies filled with countless stars bend into slow spiral arms. By ordinary logic, chaotic matter should cancel itself out, then settle into a cold, motionless mass. If every direction of motion were perfectly balanced, no invisible wheel would have enough reason to begin. If that memory of motion vanished, gas and dust would fall into each other along the shortest paths. Star-forming disks would be harder to create, matter would collide violently, and stable orbits would become much rarer. Many celestial systems would look like collapsed piles of debris instead of structures with rhythm. Yet the universe does not choose stillness. It preserves tiny imbalances and amplifies them. A very slight sideways motion can survive collisions, then grow stronger as matter contracts. From that small imbalance, a star system, a planet, even a galaxy can carry the mark of rotation. That is the rotation of the universe, the invisible wheel born from early imbalances. It faces gravity, inertia, and chaos in a negotiation that has lasted since matter first gathered. The origin of rotation does not begin with one great push, but with imperfection. In the young universe, matter was not distributed perfectly, so gravity had places to start pulling. If one region became slightly denser than its surroundings, it could draw in more gas, dust, and motion. But those streams of matter rarely fall into the center along perfectly straight paths. Each dust grain carries a small direction of its own, like a tiny memory of its first motion. When countless particles meet, many motions cancel out, but not all of them. The motion left behind is often the tiny seed of angular momentum. Angular momentum can be understood simply as the tendency to keep rotating when matter moves off-center. It needs no will and no engine, only mass and a little sideways motion. Gravity pulls matter inward, but inertia keeps part of its sideways motion from disappearing. From that struggle, straight falling motion begins to turn into circular motion. That is when the invisible wheel first appears, not as steel, but as orbit. The more matter gathers, the clearer the trace of rotation becomes, because the whole cloud must share it. The universe does not need everything to spin in the same direction. Each region only keeps its own imbalance. That is why the spin direction of celestial systems is often the result of local history. A gas cloud contains not only matter, it contains an unsorted record of motion. When it contracts, that record is not erased, but compressed into a smaller region. Like a dancer pulling in their arms, the same memory of rotation suddenly becomes faster. This is why gravitational contraction often goes together with faster rotation. From here, the story is no longer about matter falling down, but about matter learning to rotate. The first response of matter to gravity is to fall inward, but it does not fall obediently. Each stream of gas arrives from a different direction, collides, loses energy, and changes course. Energy can escape as heat and light, but angular momentum is harder to erase. That stubborn remainder forces matter to find a new structure, a rotating plane. An accretion disk appears as a compromise between falling inward and continuing to circle. Matter inside falls faster, while matter outside rotates more slowly, creating a layered rhythm. Within that rhythm, dust collides with dust, sticks together, and becomes larger grains. Larger grains pull in more material, keeping part of the rotation of the parent disk. So planets do not receive their spin from outside. They inherit it from the place where they are born. Later impacts may modify the spin direction, but they rarely create the story from nothing. Many small impacts add up, like invisible hands reshaping the spin axis of a young world. Some worlds spin upright, some tilt sharply, because their collision histories are not the same. Stars are similar. When a hot gas core contracts, leftover rotation is gathered into the star itself. But the star cannot swallow everything at once, because rotation builds a soft barrier. That barrier is not solid. It is the inertia of matter refusing to fall straight in. To fall farther inward, matter must transfer part of its angular momentum elsewhere. Through that slow exchange, the star grows larger while the disk of matter keeps rotating. From outside, this looks like a beautiful whirl. Inside, it is a physical bargain. Gravity wants to gather everything into the center, while angular momentum wants to keep everything circling. That conflict opens the way for rotating systems to become a common architecture of the universe. Once a disk forms, rotation is no longer scattered chaos, but a system. The region near the center is hotter, denser, and rotates more urgently than the cold outer edge. From that simple rule, dust knows where to gather, gas knows where to flow, and rock knows how to grow. Small bodies do not simply fall. They follow repeating curves around larger masses. Orbit becomes the way matter avoids a direct fall while still being held by gravity. A young planet both orbits its star and spins around its own axis. These two motions are not the same, but both come from the same family of gravity and inertia. Moons around planets also form from leftover matter, impacts, or small disks around their parent worlds. So rotating systems can nest inside other rotating systems, like small wheels inside larger wheels. At the scale of stars, plasma currents inside also swirl, made more complex by magnetic fields and heat. A star is not a solid ball, so different regions can rotate at different speeds. This means rotation in the universe is rarely a perfect, rigid spinning top. A galaxy also does not rotate like a metal disk. It is a sea of stars, gas, and dark matter. Stars in a galaxy follow their own orbits, but the overall shape still gives the feeling of a spiral. That rotation preserves the memory of how the galaxy gathered matter, swallowed gas, and collided in the past. The larger a galaxy is, the more its rotational story blends many gravitational encounters. Collisions do not only destroy. In the universe, they also transfer motion and rearrange spin axes. After each encounter, the new rotating system does not return to its old state, but carries another dynamic scar. That is why rotation is one way the universe stores history without writing. From dust grain to galaxy, rotating systems always need three things: mass, offset motion, and time. Mass creates gravity, offset motion creates angular momentum, and time lets that motion reorganize. None of these elements stands alone. Together, they form the silent rulebook of forming objects. That rulebook is not written on a board. It is written in the paths of gas, rock, and light. When human eyes see a glowing ring, inside it are countless exchanges still taking place. To understand why everything rotates, one must enter the part the naked eye cannot see. The central mechanism begins with a simple principle. A rotating object does not naturally stop rotating. Without strong friction like on the ground, space allows rotation to survive for a very long time. On Earth, a wheel slows because of friction. In space, resistance is usually far weaker. So motion is not erased quickly. It becomes an inheritance passed through formation. When an object's radius shrinks, the same angular momentum must fit inside a smaller space. As a result, spin speed increases, like water swirling faster as it is pulled into a drain. This is why a slow cloud can give birth to a rapidly rotating stellar core. An accretion disk is where matter solves that problem by redistributing motion. The inner part loses angular momentum, allowing it to fall closer to the star. The outer part receives more motion, spreading wider and helping the disk survive longer. Friction between layers of gas is not like a car brake, but it is enough to exchange motion. Magnetic fields can also connect matter in different regions, like soft ropes stretched through plasma. Those ropes help some rotational motion escape outward, allowing matter to keep falling inward. Inside the disk, not everything is smooth. Small vortices appear, fade, and appear again. These small disturbances keep the disk from freezing into a perfectly smooth rotating ring. A rotating system survives because it keeps adjusting, not because it rests in perfect balance. A large forming planet can carve a gap in the disk, changing the rhythm of flowing matter. It both receives material and pulls on the surrounding disk, like a stone stirring a river of dust. Gravitational resonances can gather dust into certain regions or push matter away from its path. So a disk does not merely rotate. It sorts matter by position, speed, and interaction. Once a planet has grown, tides from its star or moon can slow its rotation. Tides convert some rotational energy into heat, changing the rhythm of rotation over long periods. That is why rotation has not only a beginning, but also aging and transformation. A moon can become tidally locked, always showing nearly the same face to its parent planet. Being locked does not mean it stops rotating. It simply rotates in step with its orbit. At the galactic level, the gravity of countless masses turns the paths of stars into a vast network. There is no solid axis running through a galaxy. Only shared gravity keeps the orbits dancing together. Spiral arms are not fixed material blades, but more like density waves passing through a sea of stars. Stars enter denser regions, shine within the crowd, then continue on their own journeys. So a galaxy rotates more like a mixed symphony than a solid wheel. In many galaxies, stellar motion suggests that additional non-luminous mass is taking part. Dark matter does not need to be seen directly to influence the rotational dance of a galaxy. That turns rotation into a tool for reading the invisible, not just a beautiful sight. Observers cannot touch a galaxy, but they can measure how its light is shifted. Light from the approaching side and the receding side carries different signs of motion. Thanks to that, humans know not only that an object rotates, but how it rotates. For distant planets, tiny changes in light can also reveal spin, speed, and atmosphere. For young stars, gaps in the disk reveal where matter is rotating and gathering. For black holes, the blazing disk shows matter struggling to lose enough rotational motion. The more the mechanism is understood, the clearer the invisible wheel appears at every scale of the universe. But rotation does not only create order. If it becomes too fast, it can also become a threat. A rapidly rotating object bulges at the equator because outer material wants to fly outward. If the holding force is not strong enough, dust, gas, or rock fragments can be thrown from the system. Rotation helps a disk survive, but it also prevents matter from falling quickly into the center as gravity demands. So star formation is not a simple free fall, but a delayed process. That delay creates time for planets to form, but it also creates more chaotic regions. In that chaos, planetary embryos can collide, change orbits, or be pushed outward. A stable rotating system today may once have been a collision-filled testing ground in its youth. Too much angular momentum can cause a gas cloud to split into several separate cores. Then, instead of one lonely star, the system may give birth to a pair or group of stars. That stellar pair has its own dance, both around themselves and around each other in shared gravity. The beauty of a binary system hides a hard problem. The more motion there is, the more fragile stability becomes. If a wandering object passes near a rotating system, it can be captured or thrown away. One strong close encounter can change a planet's fate, even without leaving an explosion behind. In a disk around a black hole, the price is harsher. Matter is heated violently. Friction, collision, and compression turn the final spiral path into an extremely hot glowing region. Rotation delays the fall of matter, but also turns that fall into an energy furnace. Sometimes, energy and motion are forced into streams of matter launched from two poles. Those streams show that a rotating system does not only hold matter, it can also expel it. On gas giants, rapid rotation can stretch clouds into bands, storms, and long-lived vortices. Those cloud bands are weather-shaped by rotation, heat, and a thick atmosphere. Rotation creates large-scale order, but inside, it can feed smaller vortices that are not easily extinguished. In the universe, stability is not stillness. It is the ability to endure motion for a long time. When motion exceeds its limits, a rotating system may restructure itself through collisions, loss, or ejected matter. This leads to the central event. A gas cloud contracts and must live with its own inherited motion. Follow a vast gas cloud as a dense region inside it begins to collapse. At first, it rotates very slowly, so slowly that even nearby it would be hard to notice. But gravity does not care about slowness. It pulls every layer of gas toward the densest region. As distance shrinks, the once weak rotation begins to accelerate like a promise awakened. The central core heats up and brightens, while the matter around it cannot fall straight in. Streams of gas collide, lose energy, and are forced to settle close to a shared plane. A disk appears, growing thinner and wider, like a trace of rotation stretched flat around the young star. This is the moment the conflict becomes clear. To form a star, matter must escape the whirl. But to escape the whirl, it must hand that motion to other matter. Part of the disk becomes food for the star, while another part becomes a storehouse for planets. Dust clumps together, young rocks collide, and the first worlds gradually gain their own spin axes. No hand turns them. Small encounters write spin direction into the body itself. If a major impact occurs, the spin axis can tilt sharply, leaving a mark for billions of years. At the edge of the disk, matter is colder and moves more slowly, but the rotational story continues. Pieces of ice, rock, and distant gas create wide, long, and easily disturbed orbits. A large planet forming early can stir the whole disk, pushing smaller objects into new journeys. Some objects are thrown inward, some outward, and some become captured moons. A star system is not born like a perfect clock, but like a swirling river clearing its own path. After a long time, dangerous orbits are removed, while more durable paths survive. Final order does not deny early chaos. It is what remains after chaos has been filtered. The original gas cloud has become a star, a disk, planets, and a genealogy of motion. Every object inside spins in its own way, but all carry the trace of the first collapse. A small initial imbalance did not disappear. It became the living rhythm of the whole system. This is why rotation is not a side detail, but the backbone of the story of formation. When humans realized this, the universe stopped looking like a storage room of objects and became a record of motion. After understanding the role of rotation, astronomy began seeing dusty disks as nurseries of planets. Dark and bright rings in a disk are no longer decoration, but footprints of matter growing. Modern telescopes help reveal those structures more clearly, even though they lie very far away. Instead of only asking where an object is, observers ask how it is moving. The way light changes color because of motion becomes a key to measuring rotation from afar. Thanks to that, a distant point of light can reveal a day length, atmospheric winds, and collision history. Computer simulations also help reconstruct how a cloud collapses and speeds up its rotation. In simulations, a small imbalance can be fast-forwarded into a disk, a star, and planets. What once looked like chance gradually appears as a lawful result of physics. Scientists do not need to see the whole history. They read what remains in present motion. A tilted spin axis can suggest an old impact or a chaotic phase of formation. A misaligned disk around a binary star can tell of complex gravity between two sources of light. A distorted galaxy can reveal a gravitational encounter that once bent its stellar wheel. By watching rotation, humans measure not only speed, but memory. The modern response is not to stop the rotation, but to decode different kinds of rotation. With every newly observed star system, the old question gains another variation. Some disks are neat and round, some are torn, and some are tilted as if pulled hard. That diversity reminds us that general laws do not erase the private history of each object. The universe has rules, but every rotating system is its own record of collisions and gravitational choices. From here, common misunderstandings about rotation in the universe begin to fall away. The first misunderstanding is thinking that everything rotates because something once pushed it. In reality, most rotation is something retained, not a gift added later. The second misunderstanding is thinking that a galaxy rotates like one solid, rigid disk. A galaxy is a gravitational crowd, where each star keeps its own orbit inside a shared field. The third misunderstanding is thinking rotation always creates stability. Sometimes it is the source of instability. Rotation that is too fast can make an object bulge, tear a disk, or make orbit sensitive. The fourth misunderstanding is thinking everything in the same system must rotate in the same direction. Collisions, capture, and disturbance can create exceptions, even very strange spin axes. The final misunderstanding is thinking rotation is only a side effect and does not shape an object's fate. In reality, rotation decides where matter falls, where planets grow, and where energy escapes. It is not decoration in the universe, but one of the ways matter organizes itself. Once this is understood, the question is no longer why objects rotate, but where their rotation came from. The modern turning point is to see rotation as a fingerprint, not just repeated motion. A rotating system does not only speak of its present, it speaks of how it was born. By observing spin axes, tilts, and speeds, science can trace back many lost chapters. By observing dusty disks around young stars, science sees where unborn worlds are lining up. By observing rotating galaxies, science sees even the non-luminous mass shaping their paths. The best approach is not to force the universe into dry formulas, but to read motion as a story. Equations help with testing, but images help viewers feel the negotiation between falling and rotating. From that perspective, angular momentum is no longer just a term, but preserved memory. An accretion disk is no longer just a ring of dust, but a processing room for the fate of matter. A spiral galaxy is no longer only beautiful, it is a vast record of gravity and time. Every rotating world is a temporary answer to the question of where its matter once came from. Every exception does not break the rule. It forces deeper questions about impacts, tides, and history. The modern universe does not stand still to be observed. It always tells its story through velocity. And at every scale, the invisible wheel still leaves its mark on light. In the end, a spiral galaxy rotates slowly in the darkness, neither rushing nor standing still. In each bright arm, countless stars still carry the tiny imbalances of the beginning. The universe does not only expand outward, it also spins with the memory of matter that once gathered. The invisible wheel still turns, from the smallest dust grain to the giant bright galaxy in the night.